A majority of today will be we're going to really focus on the application of this, starting to get into what do integrals mean besides just area. Can you use them in other contexts as well? I gave you a hint about this last time when we looked at the units and how units are impacted by an integral, what a derivative does to a unit and what an integral does to a unit. What derivative does with division of units, and you just keep dividing. Integrals do with multiplication. So they allow us to apply that in other situations. In my mind, I shared with you, I think of it as going down. I don't know why, but in my brain, I think going down every time I take a derivative. And I just divide by the unit of the differential. So if it's dv dt, then I'm continuing to divide by time, divide by time, divide by time. But in integrals, we don't divide by dt anymore. We multiply. We put the dt at the end of the integral, which means we're now multiplying. So that's how we go the other way. We go up in terms of our antiderivative. So the idea there is we continue to multiply by the units of d blank, whatever d is. So dx or dt or dz or whatever units we're going to be working with, we multiply successfully. Every time you take an antiderivative, you multiply by those units. That allows us to do what's called accumulation. So we've been accumulating rectangles or trapezoids or paraboloids. We accumulate and add up a whole bunch of them. But you can accumulate any unit you want. You can accumulate time. You can accumulate bananas. You can accumulate oil, milliliters of oil. You could accumulate any unit. Okay, you can accumulate over an interval of time using integration. All right, so anytime we want to cumulative effect, we're going to integrate it. Growth, decay, consumption. So the definition of the accumulation is to use an integral over a set of bounds, you starting at a specific time of closed interval. So you always start with A. A is what we call the initial condition. I'm accumulating from here. I'm going to start measuring it from 1990. I'm going to start measuring it from, okay, so it's whatever your initial condition is. That always pops up as the lower bound. That'll always be the bottom. So that's your reference point. From that reference point, you can go forward or backward in time. You can move forward to that point, so to any future value, but you can also go back and undo things from that reference point. So, for example, water, let's take this, is pumped into a tank at a rate. Okay, so our water is being measured by a cubic function, measured in gallons per hour over the course of 3 hours. If that's the rate at which it's being pumped in, can we accumulate the total amount of water that's going to be added to the tank during that time? So we're going from a rate, which is in gallons per hour, and what would we like our answer to be in if we're looking for a total, unit-wise? If we're going from a rate of gallons per hour, what should our answer total be? Gallons. So we are trying to go from gallons per hour to gallons. So we're going to set up an integral to do that. My initial condition is time 0. I want to go over the course of 3 hours. I'm going to look at the function w of t, and then my differential will be over the course of dt. So looking at units, w of t is in gallons per hour, whereas time is in simply hours. So when you multiply the gallons per hour times the hour, my result is going to be that the hours cancel each other out, and my answer is going to be in terms of straight out gallons. So then we would have, all right, this is going to be the integral from 0 to 3 of the cubic equation, t cubed minus t plus 2 over the course of the time axis. Then to evaluate that, your method is going to depend on whether or not you have your calculator accessible to you or not. If this is a calculator one, then you're just going to grab your calculator and you're going to go ahead and plug this as a Math 9 expression. Doesn't matter that it's t, your calculator can handle that. That's irrelevant, the value of the variable. Okay, you'll just enter it as x, and that's fine, because it's just a horizontal axis. If you don't have a calculator, then your only other option is what method? Antiderivative. So it'll be depending on, is this a gray or not gray? Let's assume you have your calculator. Go ahead and grab it out and evaluate the Math 9 value for this. All right, so we're looking at a value then of 21.75, and then the gallons are the unit. Every time you forget the unit on an application problem where you were given units, it will be a penalty. It's not a lot, but it starts to add up every time you forget it. Okay, we're gonna try another one. This time our initial condition begins. A quick read will tell you in what year? 1970, okay? So from 1970 to 1980, potato consumption in a particular country was C of t, and now we're looking at an exponential function. So 2.2 plus 1.1 million bushels per year, with time being the years since 1970. How many bushels were consumed from the beginning of 72 to the end of 75? Okay, the beginning of 72 to the end of 75. All right, so we are going to set up an integral to model this. We'll be looking at the C of t. Okay, and the C of t is measuring in millions of bushels per year. dt will be my differential. And then what are my bounds? Oh, okay, so dt will be measured in years since the beginning of 1970. What will my bounds be? What will my lower bound start out as? 2. And the upper bound? No. Okay, now you gotta be a little bit careful. One says the beginning of 72, the other says the end of 75. So you can't, you have to make the language the same. So if the beginning, either make them both say the end of something or make them both say the beginning of something else. So let's go with the beginning of 72, and the end of 75 is really the beginning of what year? 76. Okay, so you do have to convert your time so that the language is the same, so that you are getting the right number of years. Because we want to be able to count the correct number of years. So it's going to be 2 to 6, not 2 to 5. Another way, just use your fingers, right? 1972, 73, 74, 75. I need to cover 4 years worth. If I only did 2 to 5, I'd only be covering 3 years worth. Yeah.
Is it acceptable then to go from 0 to 4?
No, because then that would be you're going to have different total. That'll give you the total from 1970 to 1974.
Okay. Why is it okay then to move it from 1972 to 1975 and put that into 2 to
Because
6?
the end of 1975 would be December 31st, 1975, which is only 1 day away from January 1st, 1976.
I understand now.
Oh, okay.
But those are like big years. How is that acceptable to change into 2 and a 6, but you can't change the 2 and a 6 to a
0 to 4?
0 to 4, yeah.
Well, just for example, what would you get if you plugged 0 into your equation?
Like 3.2.
0 on 1.1 to the 0. What's anything to the 0 power? 1, right? So you're going to get 3.2.
Yeah.
All right, so that represents 3.2 million.
Okay.
If you plugged 2 into that equation, you're going to get a very different number, which means you won't be starting at the same amount. And exponentials are not. If it was linear, I would have no problem with what you're doing. But we're not doing linear. We're doing exponential, and the exponential is very different from a 0 compared to a 2, compared to a 4, compared to a 6.
Okay.
They are very different. All right, so we're going to set this up. Good questions, though. So we're going from 2 to 6 of our exponential. So 2.2 plus the 1.1 to the t dt. And again, because this is an exponential function, we would need, you could do it without. It would be messy, but you do know how to do an antiderivative of 2.2, and you do know how to do an antiderivative of an exponential 1.1, but it'll involve the natural log. So it does get messy. So you'll likely have your calculator here going from 2 to 6. And that turns out to be 93.892, which is not just the number of bushels, but the number of millions of bushels of... Oh, I did 22 instead of 2.2. I missed a decimal. Sorry. About 14.692. Better? All right. Potatoes. Anybody know what a bushel is? Not one plant of potato. No. Okay, a bushel, there's a bushel basket. A bushel basket is this like woven basket that has handles on it. It's kind of round. Kind of like, you know those red rubber things that they put drinks in, like a beverage tub? Can you picture that? That's probably a little bit bigger than a bushel basket. So that was what they used to measure a bushel of peaches or a bushel of corn or whatever. So they measure that as a bushel. I don't know what it translates into pounds.
Those units do good.
Millions of bushels of potatoes.
On the quiz, I got marked down for not putting years.
During, yes, thank you. From. And it depends on if the questions say, like in the context of the question, what are.
Because, yeah, it's not. It also explain it.
Yeah, it depends if they say explain using units, then you would want to cover everything. If they just say how many, then we're just going to answer how many.
This question is not.
How many? So then we wouldn't have to.
That's not what I understood on the quiz. So
Okay.
that makes sense.
All right. In terms of physics, the idea, we're getting back now to displacement. Displacement is another word for net. What is the net distance? Okay, so if you're a track runner out running the 440 or whatever, okay, your net distance is 0 because you end up in the same place that you started, or 400. You end up, your net is 0, but trust me, those 2 minutes were a long burn as you're out there running, okay, as opposed to total distance. So total, we need to make sure that we have the absolute values around anything that is negative. If you are asked about the final position, where do you end up? That question often gets confused with total distance. Often people will say, they'll answer final position as the same thing as total distance. It's not. You have to take into account that initial starting position affects your final position, so it's the initial starting position and the displacement combined will tell you where your final position is. The only time that the final position will be equal to its displacement is if your initial starting condition happens to be 0. That's the only time those two things will be equal. Otherwise, your final position is different. So maybe you have a head start, or maybe you're not starting right at wherever ground 0 is. Or maybe you're launching from a platform that's not on the ground, or maybe you're launching from the top of a hill. Okay, so your final position ends up to be different. All right, so let's take a look at this. This question is a physics question, but this time that we're directed to use analytic methods. So that means no calculators, so we put our calculators away, and everything we're going to be doing now is done by analysis. So our velocity here is given as a linear. Linear is the velocity measured in meters per second of a particular particle moving along the x-axis from time 0 to 9. Use analytic methods to do all of the following. So this is a combination of everything from last semester and this semester. Determine when the particle is moving to the right, to the left, and stopped. Then find the particle's displacement for the given time interval. So part A, determining left, right, and stopped, that harkens back to first semester. To do that, we want to set what equal to 0? Set velocity equal to 0. We already have velocity. Velocity was given to us. So in part A, we'll take 10 minus 2t. We'll set that equal to 0, which is going to give me t equals 5. That tells me when my particle is at rest or stopped. So my particle has no velocity at that point. Then I want to set up an interval at that critical point of 5 from the beginning of the time interval to the end of the time interval, and then test for the direction. So I choose that sample value. Okay, good times, good memories back here. So we'll pick a value between 0 and 5. We'll check that in the value. Say you pick the number 3, you turned out that the velocity is positive, and then you pick the number 7, and it turns out the velocity is negative. So we can determine when our particle is moving to the right, to the left, and when it stopped. It doesn't say we have to justify our answer, so we don't need complete sentences for this particular one, but we've got right, we have left. Okay, the particle's displacement. Part B. The definition of displacement is the same as the definition of net. So my displacement is simply the integral from 0 to 9 of 10 minus 2t dt. Now, since we don't have our calculator, we have two other choices here to do at this point. We could use geometry if geometry was good for us, or we could do antiderivative, so your choice. If you decide to do geometry, you're going to have a couple different triangles because 10 minus 2t is simply a linear function that crosses at the number 5. So you could do those triangles that way. Those are not symmetric triangles. Mine maybe look like they are, but they're not symmetric. So you could do triangles if you wanted. This is 10. So you've got one triangle there. If we plug 9 in, we have negative 8. We have another triangle there. So you could do geometry, and you're just keeping the negative, and keeping the positive. Do you expect this? I know mine looks kind of symmetric, but do you expect the answer to end up with more positive or more negative? Should be more positive, slightly larger triangle. So you could do it with geometry. Or if you feel like geometry is not your strength or drawing is not your strength, then you could also show the work of doing an antiderivative. And so you'd have 10t minus t squared plus c going from 0 to 9. You can do it that way. So that would give you 90 minus 81 plus c minus 0. So you're looking at 9. You have to show c at least one, like you don't even have to do like both of this one and this one, but at least once it has to be in there. So at least maybe for sure get it in there. Okay. And that's just, you don't have to always show it all the way through, but at least one time you have to show the person who's reading it that you know that it is there. All right, now I want units on this. So looking at what the units were that I was given, considering what the time units are, what will my units for 9 be? Okay, meters. And so my displacement means that I've traveled 9 meters. Now, does that mean that my object is sitting at position 9 meters? Do we have enough information to know that right now?
Yes.
Okay.
On the x-axis.
Well, we know it's moving on the x-axis, but what piece of information are we missing?
Initial.
We don't know where it started on the x-axis. The only way it would be sitting at 9 on the x-axis is it started at 0, and we don't know what its initial position is yet.
Wait, so sorry, we don't know its true displacement then?
We know its displacement. We don't know its position.
Oh, right.
Okay? We know it's traveled 9 meters, but 9 meters from where?
Okay.
Right? Okay, so now, part C. If S of 0, that's the position at 0, is 3, so now we have the starting position. What is the particle's final position? So we do have the starting value, and so we would, okay, 3 plus 9, it's actually sitting at 12 meters when we take those two things into account. All right, finally. Find the total distance traveled by the particle. So now we need to take into account the negative. So again, you have two options at this point. You can go back to your geometry and you can say, well, I had 0 to 5 with a triangle of 10, and then I'll have the rest of it. I'll have this, I can think of it that way as two triangles, and you make the negative triangle positive, so you can do it that way. Or you use absolute value. So your absolute value would be setting up one integral that goes from 0 to 5, and that would be 10 minus 2t dt. And then a second integral going from 5 to 9 and putting the absolute value around that and going from 10 minus 2t to dt. This is a situation where me personally, I feel like now the geometry is easier because otherwise I have to do two antiderivatives and I have to worry about the absolute value, but we can do both. So we'll have 1/2 base times height, so this would have a area of 25, and then 1/2 base times height, so that would have an area of 16, so 25 and 16 giving me a total distance of 41. With the integrals, if you didn't want to do geometry, you have to pre-write your second integral. So you can do it a couple ways. We know that it was below the x-axis, so it's going to be negative. One way to take something that's below the x-axis and make it be positive is to run your bounds backwards. Right? Because we know it's already negative, and if we run our bounds backwards, that's going to give me another negative. So I can switch my bounds from 9 to 5 and then go from 10 minus 2t dt. So that would be one option. But then your work's going to have to be, all right, 10t minus t squared plus c from 0 to 5. And then 10t minus t squared plus c from 9 to 5, and then evaluating it that way.
Wait, you want to go 5? No, because you're taking the negative. Oh, yeah.
Taking the negative of, if I go from 5 to 9 without changing anything else, I'll have negative, I'll get the same answer that I got last time. I need to make sure that I'm making this positive. So 50 minus 25 plus c minus 0 plus c. That's the first integral. And then 50 minus 25 plus c minus 90 minus 81 plus c. So I'm going to get 25 plus 25 minus 9. Still equals 41, the same way I did the other way. So even just looking at it, you're like, geometry easier in this one. But play to your strengths, what your strengths are. Okay, we only have one more example. Yeah.
Why is it positive 8? Because if you're plugging 9 in, it comes out negative 8. Where does
Why is it-
positive 8 come from?
Because I took what wasn't, because I'm dealing with absolute value, I took the triangle that was below the x-axis and I reflected it above the x-axis. Now it's positive 8, so that I could think of the absolute value of that area instead of where what used to be. I could do it like this too. There was a negative triangle underneath that. Okay, but when you do things that are absolute value, you flip them above the x-axis. All right, last one. What if you do the exact same thing, only instead of starting with a linear, you start with a parabola? Okay, the exact same thing, but instead of starting with a linear, so you're not going to have nice triangles anymore, you're going to start with a parabola. So by making it a parabola instead of and taking away triangles as an option, what option have I also really essentially taken away? Any geometry. Okay, this is forcing you. Now you have, the only way you have is the antiderivative.
Would you do a bunch of rectangles and just do a lot of them?
No, we'll use our antiderivative.
Oh, sorry,
Yeah.
if you were to try to get a correct geometric.
You couldn't get a correct one. You could get close, but you'd have to do 24 rectangles or 99 rectangles, or it would take a lot. All right, so instead we want to find out again when it's moving to the right, left, or stopped. So we're going to take our setting our velocity equal to 0 again. So part A, I'll take 10 minus 2t squared. Set that equal to 0. That gives me that t is plus or minus the square root of 5. Of course, I'm going to throw out the negative one because I'm only going for the values that are between 0 and 9. So I'll have 0 up until the value of rad 5, and then rad 5 up until 9. And we'll test again. So I'm going to pick the number 1. Number 1 gives me a positive value for my velocity, and I'll pick the number, I don't know, yeah, 5. Okay, that'll give me a negative. So now I know when it's stopped and when it's going from the right and to the left. So now I want to find the particle's displacement. Even just thinking about the graph of this does. Okay, I do have now a parabola for a graph. So I can't do geometry, but I can at least still consider, what do you expect the answer to be? Should be negative, because there's way more negative area than on the parabola than there is positive. All right, so then we're gonna, bless you, find our displacement using the antiderivative. So our displacement will go from 0 to 9 simply with the parentheses of 10 minus 2t squared dt. So my antiderivative is going to be 10t minus 2t cubed over 3 plus c, and then going from the 0 to 9. So that'll be, starting with the number 9, 90 minus 2/3 of 729. 720. Did I do that right? 81 times, yeah, okay.
Yeah.
Okay, plus c minus 0 plus c. It's gonna be a big negative number. 83, so 90 minus 166, So negative 76. I divided, oh, no, not 83. Do my division right. 243, that's better. So an even bigger negative number and an even bigger negative number. 486. So 294. 394. 394. 390. Can't even do my math this morning. 396 meters. Again, not enough to know where its final position is. So if our starting position was number 3, so we've had 3 plus negative 396. So we're looking at negative 393 meters. All right, total distance. To find the total, we're going to separate this into 2 integrals. So we'll go from 0 to rad 3 of 10 minus 2t squared dt. Rad 5, I had it in my head. And then from rad 5 to 9 of the absolute value of 10 minus 2t squared dt, which really means I like running the bounds backwards. There is another, you can multiply the whole thing by negative if you prefer, but my preference is to run my bounds backwards. It's really up to you. But you do have to know which section is negative so that you know which one to run your bounds backwards on. If you have a calculator, then you get to avail yourself of that. Otherwise, you're just going to do the same antiderivative you had before. And this will be an irrational number because we're dealing with the rad of 5. So we have 2 separate antiderivatives, or the same antiderivative, but 2 separate intervals. So looking like 10 rad 5 minus 2/3 of rad 5 cubed plus c minus 0. And then the same thing and then minus 90 minus that same 2/3 of 9 cubed plus c that we had before. Then it just becomes arithmetic, which apparently I'm a little rusty on this morning. I would probably group some of the like terms together. I would notice that I've got a 10 rad 5 and another 10 rad 5 that are being added together, so that'll give me a 20 rad 5. I've got 2 of the minus 2/3 rad 5 cubed, so that would be minus 4/3 rad 5 cubed. And I've got the 90, and then the double negative, if I distribute it, turns it back to, I think it was 486, if I remember on the other one we did, right? Yeah, 486. You also can simplify rad 5 cubed. Here's a math trick on that one. Rad 5 cubed is the same as rad 5 squared with another rad 5. I like separate it into 2 of one and 1 of the other. What can I do to the rad 5 squared then? Times a 5 and then multiply it by the 4/3. So that would simplify to make 20/3. So now I've got, these are like terms as well, 20 rad 5s minus 20/3 rad 5s. That would be something I could do, plus 396. So there are ways to simplify this. But altogether we end up with 40 thirds rad 5 plus 396 meters. That's about as good as I can get. You're hoping for not very many of these.
Wait, how'd you get 20 thirds, is that, 40 thirds?
I got a common denominator between 20 and 20 thirds, so I think that's 60 thirds is the same thing. So I did 60 thirds minus 20 thirds. I'll just